Welcome, dreamers, to this quiet hour where time slows and the stars draw near. If you've come here with a restless mind or a heart heavy with the weight of earthly concerns, let us gently untether from the gravity of today and drift together toward a moment when all of humanity held its breath as one. Tonight, we return to July 1969, not with the roaring thunder of rockets, but with the soft focus of memory. We'll wander through the silent spaces between history's grand gestures, where the true poetry of Apollo 11 lives, in the hush before ignition, in the static-laden pauses between spacecraft and Earth, in the intimate creak of a lunar module settling onto untouched dust. This is not just a story of engineering triumph, but of three human beings suspended between worlds, carrying with them the quietest hopes and fears of our species. Picture, if you will, the spaces between the milestones. Neil Armstrong's unspoken thoughts as he descended that ladder into alien sunlight. Buzz Aldrin's measured breaths as he became the second soul to touch another world. Michael Collins' solitary vigil in lunar orbit. The loneliest human in existence, cut off from all contact as he passed behind the moon. Imagine the scent of hot metal and oxygen circulating through the cabin, the way dust motes might have floated in the sunlight streaming through the command module windows, the peculiar weight of a pen left floating mid-air when released. Before we slip deeper into the celestial reverie, I wonder, where does your mind linger when you think of that summer night? Do you see the flickering television screens in living rooms across the world? Or the mathematicians with their slide rules working through the night? Perhaps you imagine the moon itself, ancient and unchanged, suddenly feeling the feather-light pressure of human footsteps after eons of stillness. Wherever your thoughts alight tonight, I'm glad you've joined me. So let's breathe together, in and out, and allow the boundaries between past and present to blur. Let the glow of your screen soften like earthshine on the lunar module's foil-wrapped curves. We're about to retrace a journey where every moment balanced between miracle and disaster, where human ingenuity danced with cosmic uncertainty, and where the most extraordinary achievement somehow felt in that magical hour like the most natural thing in the universe. The stars are brighter beyond our atmosphere, the silence deeper, and the story, though you may know it well, still hums with secrets in its quietest corners. Shall we listen? Let's begin. The night sky has always whispered to humanity in a language of silent wonder, its dark expanse punctuated by the gentle glow of distant stars and the luminous face of the moon. For centuries, that silver disk hung just beyond our reach, a celestial companion whose pockmarked surface told stories of cosmic violence and ancient stillness, visible yet untouchable. Then, on a July evening in 1969, the impossible became real. A spacecraft named Apollo 11, the product of 500,000 working hands and the collective imagination of an entire generation, carried three humans across the void to that distant world, and in doing so, rewrote the story of what it means to be an earth-bound species daring to reach beyond our cradle. The journey of Apollo 11 did not begin with the roar of engines at Cape Kennedy, nor even with President Kennedy's bold declaration in 1961 that America would send a man to the moon. It began in the quiet corners of human curiosity, in the observations of ancient astronomers tracking lunar cycles, in the sketches of Renaissance dreamers who imagined winged ships sailing through the heavens, in the equations of 19th century physicists who first understood the forces that would one day make spaceflight possible. By the mid-20th century, these fragments of inspiration had coalesced into something tangible, the understanding that the moon was no longer just a light in the sky, but a destination. To grasp the magnitude of what Apollo 11 achieved, we must first understand the machine that made it possible, the Saturn V rocket. It was a leviathan of engineering, a structure so immense that standing at its base felt like standing at the foot of a steel canyon, its body stretching 363 feet toward the sky. 5 F1 engines, each capable of gulping 3 tons of fuel per second, would awaken with a fury that shook the Earth for miles, generating 7.5 million pounds of thrust, enough to lift the equivalent of 10 nuclear submarines off the ground. Yet, for all its raw power, the Saturn V was also a masterpiece of precision. Its 3 stages had to separate at exactly the right moment, its trajectory calculated to account for the Earth's rotation, the moon's gravitational pull, and the subtle nudges of solar radiation. A single error in timing or angle, and the spacecraft could miss the moon entirely, condemned to an endless orbit in the dark. Nestled at the top of this towering machine were the spacecraft themselves, the Command Module Columbia, a cramped but sturdy capsule where the astronauts would spend most of their journey, and the Lunar Module Eagle, a fragile-looking craft that would carry 2 of them down to the moon's surface. These were not just vehicles, but life-supporting bubbles of Earth, carrying with them the right mix of oxygen, the right pressure, the right temperature to keep 3 humans alive in an environment that wanted nothing more than to kill them. Every square inch of these modules had been debated, tested, and retested. The switches, the wiring, the heat shields that would protect them during re-entry, blazing through the atmosphere at 25,000 miles per hour. But before any of this could happen, before the rocket could be assembled or the astronauts trained, engineers had to solve problems that had no precedent. How do you build a computer small enough to fit inside a spacecraft, but powerful enough to navigate to the moon when the most advanced machines of the time filled entire rooms? How do you shield astronauts from the deadly radiation of the Van Allen belts or the micrometeoroids streaking through space like invisible bullets? How do you design a spacesuit flexible enough to allow a man to walk, kneel, and work on the moon, yet strong enough to keep him from boiling in the sunlight or freezing in the shadows? These were the quiet, uncelebrated challenges that occupied the years before Apollo. The kind of work done in wind tunnels and vacuum chambers, in midnight meetings where coffee-stained blueprints were spread across desks, in the minds of mathematicians who knew that a single overlooked decimal could mean catastrophe. And then there were the unknowns, the things no one could predict. What would the moon's surface be like? Would it support the weight of the lunar module, or would it swallow it like quicksand? Would the dust cling to the astronauts' suits, clogging their equipment? Would the strange lighting of the lunar landscape, with no atmosphere to scatter the sunlight, make it impossible to judge distances? These questions haunted the mission planners, and so they prepared for every conceivable disaster. They built simulators that recreated the moon's gravity, trained the astronauts in underwater tanks to mimic the sluggish movements they would experience in their bulky suits, and drilled them relentlessly on emergency procedures. Neil Armstrong, Buzz Aldrin, and Michael Collins spent hundreds of hours in these simulations, rehearsing not just the ideal mission, but every possible way it could go wrong until their responses became instinct. As we begin this journey through the story of Apollo 11, let us not rush ahead to the moment of triumph, the first footstep, the flag planted in the dust. Instead, let us linger in the years of toil that made it possible, in the quiet dedication of those who saw not just the glory of the goal, but the beauty of the problem-solving required to reach it. For the true wonder of Apollo 11 lies not just in the fact that we reached the moon, but in how we did it, with ingenuity, with persistence, and with a collective determination that, for a brief moment, united the world in awe. the Apollo program was not merely a feat of engineering. It was a symphony of human intellect with thousands of scientists, mathematicians, and technicians, each contributing their expertise to solve problems that had never before been encountered. At the heart of this endeavor was the guidance computer, a device so advanced for its time that it pushed the boundaries of what was thought possible in computing. In an era when computers filled entire rooms, the Apollo guidance computer was a marvel of miniaturization, compact enough to fit inside the spacecraft, yet powerful enough to navigate the vast emptiness between Earth and the Moon. The AGC was a triumph of innovation, built with circuitry that was cutting edge in the 1960s. It had a mere 64 kilobytes of memory, less than a modern digital watch, and operated at a speed that would seem glacial by today's standards. Yet, this unassuming machine was entrusted with the lives of the astronauts and the success of the mission. Every calculation, every trajectory adjustment, and every critical maneuver relied on its flawless performance. The software, painstakingly woven by hand by a team led by Margaret Hamilton, was so robust that it famously saved the mission during the lunar descent when the computer became overloaded with data. Instead of crashing, it prioritized essential functions, allowing Armstrong and Aldrin to land safely. This moment was a testament not just to the machine's design, but to the foresight of the engineers who anticipated failure and engineered resilience into every line of code. But the computer was only one piece of the puzzle. The spacecraft's navigation system was another masterpiece of ingenuity. Without GPS or the familiar landmarks of Earth, the crew had to rely on a combination of star sightings, inertial measurement, and radio signals from Earth to determine their position in the void. The sextant, a tool borrowed from centuries of maritime navigation, was adapted for space, allowing the astronauts to take precise measurements of the angles between stars and the horizon of the Moon or Earth. These measurements, fed into the AGC, enabled the spacecraft to stay on course with astonishing accuracy. It was a delicate dance between human skill and machine precision, each complementing the other in the unforgiving environment of space. The challenges extended far beyond navigation. The spacecraft had to withstand extremes of temperature, from the blistering heat of unfiltered sunlight to the deep cold of shadowed space. Engineers developed a thermal protection system using layers of specialized materials, including gold foil to reflect solar radiation and ablative shielding to dissipate the intense heat of re-entry. Even the paint on the spacecraft's exterior was carefully chosen to balance thermal properties with weight constraints, as every ounce mattered in the calculus of escape velocity. Then there was the question of propulsion. The lunar module's descent engine had to be throttleable, a rarity in rocket design, to allow Armstrong to manually adjust thrust during the final critical moments of landing. This engine was a masterpiece of control, capable of firing precisely enough to lower the module gently onto the Moon's surface without toppling it or kicking up excessive dust. The command module's engine, on the other hand, had to be utterly reliable for the return journey, as a single failure would strand the crew in lunar orbit. Redundancies were built into every system, and each component was tested to the point of destruction to ensure it would perform when needed. Amid these technical marvels, it's easy to overlook the human element. The astronauts themselves were engineers, test pilots, and scientists, trained to understand their spacecraft as intimately as the people who built them. They spent countless hours in simulators, rehearsing every phase of the mission until their actions became second nature. They learned to interpret the subtle hums and vibrations of their craft, to diagnose problems under pressure, and to improvise solutions when the unexpected arose. Their training was so thorough that when alarms blared during the lunar descent, Armstrong and Aldrin remained calm, trusting their instincts and their machine to see them through. As Apollo 11 hurtled toward the moon, it was not just a machine carrying humans, it was the culmination of centuries of curiosity, decades of innovation, and years of relentless preparation. Every bolt, every circuit, every line of code represented a triumph over doubt, a refusal to accept the limits of the possible. And as the world waited breathlessly, the spacecraft and its crew pressed onward, a fragile bubble of life and intelligence moving through the silent expanse of space toward a destination that had once been nothing more than a dream. As Apollo 11 slipped free from Earth's embrace, the spacecraft entered an eerie quietude unlike anything experienced on our bustling planet. The roar of the Saturn V's engines faded into memory, replaced by the perpetual whisper of oxygen circulating through the cabin, and the occasional metallic creak of the spacecraft adjusting to the temperature swings of space. Outside the small windows, the crew watched their home planet shrink into a delicate blue marble suspended in the infinite black, a perspective no human had ever witnessed firsthand before. This tranquil yet profound leg of the journey, the 3-day cruise toward lunar orbit, masked an intricate celestial dance governed by Newton's immutable laws and monitored with watchmaker precision by mission control. The trajectory to the moon was not a simple straight line, but rather a carefully calculated curve that accounted for both Earth's gravity letting go and the moon's gravity taking hold. Engineers had to solve what they called the three-body problem in real time, constantly making minute adjustments to account for the gravitational pulls of both celestial bodies while maintaining course with fuel efficiency in mind. The spacecraft essentially fell toward the moon in a controlled manner, its path refined by mid-course corrections, so subtle they would barely disturb a feather in zero gravity, yet so crucial that missing the proper approach angle by even a fraction of a degree could send the capsule hurtling past the moon into endless space. Inside Columbia, the command module, time took on a different quality. Without the familiar cycle of sunrises and sunsets, just 90 minutes apart in low Earth orbit, the astronauts followed an artificial schedule maintained by their Omega Speedmaster watches, the only timepieces certified for spaceflight. They ate rehydrated meals from plastic pouches, slept in floating restraint harnesses, and performed routine system checks that kept their fragile life support bubble functioning. The quiet monotony was punctuated by moments of wonder: Earthrise over the lunar horizon, the first time any humans had witnessed this phenomenon from such proximity, and the surreal sight of the moon growing larger each hour, its craters and plains coming into sharp relief. The most delicate maneuver came when Apollo 11 reached the moon's sphere of influence. The spacecraft had to fire its service propulsion engine precisely at the right moment to slow down enough to be captured by lunar gravity, what engineers called lunar orbit insertion. Too much braking force, and the craft might crash into the moon. Too little, and it would sail right past. As the engine ignited behind them, the astronauts watched through their windows as the lunar surface, previously below them, appeared to rise up and surround them, an optical illusion caused by the change in their orbital path that made it seem as though the moon was swallowing them whole. Success meant entering what Michael Collins would later call the loneliest place in existence, lunar orbit. Here, the spacecraft circled the moon every 2 hours, alternating between periods of blinding sunlight and profound darkness. During the dark passes, the only illumination came from the soft glow of instrument panels and occasionally the eerie phenomenon of earthshine, sunlight reflected off their home planet, gently illuminating the lunar landscape below with a blue glow. It was in this silent realm that the mission's most critical separation would occur, the undocking of the lunar module Eagle from the command module Columbia, leaving Collins alone in orbit, while Armstrong and Aldrin descended to make history. The technology enabling this separation was both simple and brilliant. A series of latches and springs designed to work perfectly in the absence of gravity, tested hundreds of times on Earth, but only now being put to the ultimate test. As the two spacecraft parted, Collins performed a slow pirouette in Columbia to visually inspect Eagle, ensuring no damage had occurred during the journey. Seeing the strange, spidery lander floating against the stark backdrop of the moon, he later remarked was like watching some prehistoric bird poised for flight. Meanwhile, inside Eagle, Armstrong and Aldrin powered up systems that had lain dormant since launch. The lunar module was the most specialized vehicle ever built, useless in Earth's atmosphere, incapable of returning home, designed solely to descend from orbit to the lunar surface and then ascend back to orbit. Its angular shape and gold foil wrapping gave it the appearance of some ancient, sacred object, yet its 4 landing legs and intricate thrusters represented the pinnacle of 20th century engineering. As they prepared for powered descent, the moon filled their windows completely, its surface features rushing by at an alarming speed. The tranquility of orbit was about to give way to the most perilous phase of the mission, one where split-second decisions would mean the difference between triumph and tragedy. The lunar module's guidance computer flashed numerical codes that the astronauts had memorized through countless simulations. Below them, the landing site they had studied for months in photographs now revealed itself in real time, but not as expected. The computer was taking them toward a field of boulders the size of small houses, and Armstrong's calm voice crackled over the radio with words that would become legend. "We're going to need to find a better spot." In that moment, all the preparation, all the engineering, all the simulations came down to human judgment. Armstrong's piloting skill, Aldrin's rapid calculations, and their shared ability to remain focused while fuel dwindled and alarms sounded. As the dust kicked up by their engine obscured the surface in the final moments, the lunar module's shadow suddenly appeared beneath them, their first clear visual cue to altitude. Then came the gentle thud of contact, the dust settling to reveal a landscape untouched by life, unchanged for eons, now bearing the weight of human presence. The silence that followed was perhaps the most profound in history. 2 men breathing heavily in their suits, the faint hum of electronics, and beyond their metal walls, the absolute quiet of an airless world. They had arrived. The moment the lunar module Eagle settled onto the Sea of Tranquility, time seemed to pause. Inside the cramped cabin, Neil Armstrong and Buzz Aldrin sat motionless for a few heartbeats, their eyes scanning instrument readings to confirm what their bodies had already sensed: they had landed. The dust kicked up by their descent engine swirled outside the windows like a slow-motion snow globe before settling with unnatural speed, revealing a landscape of grays and blacks so stark it looked more like an abstract painting than a real place. There was no sound of wind, no creak of cooling metal, just the hum of electronics and the rhythmic sound of their own breathing inside their helmets. They were sitting on the surface of another world. Armstrong's first words after landing, "Houston, Tranquility Base here, the Eagle has landed," belied the tremendous tension of those final descent moments. What the world didn't hear was the rapid back and forth between the astronauts in those seconds before touchdown, the clipped technical jargon masking their racing hearts as Armstrong manually piloted past the boulder field with less than 30 seconds of fuel remaining. Now, with the adrenaline ebbing, they faced a new challenge, preparing to exit their metallic cocoon and step into history. The process of suiting up for the lunar surface took longer than anticipated. Every movement in the cramped cabin required careful coordination, 2 grown men in bulky pressure suits maneuvering in a space no larger than a small bathroom. They depressurized the cabin, then slowly opened the hatch to reveal a view no human eyes had ever seen firsthand: the lunar surface from ground level. Armstrong, positioned near the opening, would be first to exit. As he backed down the ladder, his movements were transmitted to Earth via a black and white television camera activated by a pull cord, an ingeniously simple solution to what engineers had worried would be a complex deployment mechanism. Then came the moment the world had been waiting for. At 10:56 p.m. Eastern Daylight Time on July 20th, 1969, Neil Armstrong placed his left boot on the lunar surface. His words, "That's one small step for man, one giant leap for mankind," would become among the most famous ever spoken, though the audio crackle obscured his intended A before man, slightly altering the meaning. What cameras couldn't capture was the physical sensation Armstrong experienced in that moment, the strange combination of lightness and the surprising resistance of the lunar dust as it compacted under his weight. Aldrin joined him shortly after, describing the view as magnificent desolation, a perfect encapsulation of the moon's paradoxical beauty. Their first tasks were methodical, collecting a contingency soil sample immediately in case they needed to abort, photographing the landing site, and deploying the early Apollo scientific experiments package. These instruments included a passive seismometer to measure moonquakes and a laser-ranging retroreflector that would allow precise measurement of the Earth-Moon distance for years to come. The astronauts moved with cautious enthusiasm, their bulky suits requiring deliberate movements. They discovered that the famous bunny hop wasn't the most efficient mode of locomotion. A sort of modified lope worked better in the low gravity. Every action produced unexpected results. Dust kicked up by their boots didn't billow, but instead followed perfect parabolic arcs. Tools dropped fell slowly, but didn't float away as they might in zero gravity. Their footprints compressed the lunar regolith into surprisingly crisp impressions that would remain undisturbed for millennia. Perhaps the most profound moment came when Armstrong and Aldrin paused from their checklist to simply look around. Before them stretched a landscape untouched by erosion as we know it, where every crater and rock told a story billions of years old. The sky was the deepest black they'd ever seen, yet the surface around them glowed in the sunlight with an almost metallic sheen. Earth hung in the sky like a delicate blue and white marble, the only spot of color in this monochrome world. In that moment, the two men experienced a perspective shift later described by many astronauts as the overview effect, the sudden realization of Earth's fragility and unity when seen from space. Their time outside was limited, just 2.5 hours, but packed with activity. They planted the American flag, took core samples, and photographed everything from panoramic vistas to minute soil details. All the while, their life support systems hummed quietly, recycling oxygen and cooling their suits against the 250-degree Fahrenheit temperature swings between sunlight and shadow. As they prepared to re-enter the lunar module, they left behind not just experiments and a flag, but symbolic items, including a silicon disc containing goodwill messages from 73 world leaders, Apollo 1 mission patches honoring the astronauts lost in the 1967 fire, and a gold olive branch, Armstrong's personal choice to represent the peaceful nature of their mission. The last thing they did before closing the hatch was look around one final time, knowing they would likely never return to the spot that had witnessed such a monumental human achievement. Inside Eagle once more, the astronauts faced the surreal task of preparing to sleep on the moon. With no beds or sleeping bags, they would rest in their suits, loosely tethered to the cabin. The reality of their situation must have been overwhelming. Two humans about to close their eyes while perched on the surface of another world, separated from home by nearly 250,000 miles of empty space. As they settled in, the only sounds were the mechanical noises of the lunar module's systems, and, if they listened carefully, perhaps the faint creaks of metal adjusting to the extreme temperature changes outside. The first lunar day was complete. The pale glow of lunar dawn crept across the Sea of Tranquility as the Eagle's systems hummed back to life. Inside the cramped cabin, Armstrong and Aldrin prepared for the most critical maneuver of their mission, the ascent from the lunar surface. Unlike the controlled descent, this launch would have no second chances. The lunar module's ascent engine had to ignite perfectly on the first attempt, lifting them off the moon with just enough precision to rendezvous with Collins orbiting above in the command module Columbia. There were no launch pads here, no teams of engineers monitoring readouts, just a single ignition switch, and the laws of physics determining their fate. As Aldrin counted down, Armstrong's finger hovered over the switch. The engine fired with a startling burst, lifting Eagle upward in complete silence. No roar of combustion, no vibration through the cabin, just the sudden sensation of movement in the airless void. Through the windows, the astronauts watched as their landing site fell away, the flag they had planted now lying flat where their exhaust had knocked it over. The ascent was a ballet of mathematics made physical, their trajectory calculated to intersect Columbia's orbit at the exact moment Collins came around the moon's far side. One small error in angle or timing, and they might sail past their only ride home, condemned to circle the moon until their oxygen ran out. Meanwhile, Michael Collins had spent what he later called the longest 22 hours of my life, orbiting alone. His solitary vigil took him around the moon's far side every 2 hours, cutting off all communication with Earth and his fellow astronauts below. Each pass brought alternating extremes: blinding sunlight that turned Columbia's interior into an oven, followed by frigid darkness that left condensation forming on the instrument panels. Collins later admitted that despite his training, he couldn't shake the irrational fear that he might emerge from the moon's shadow to find mission control silent, the world below having given up on them during his absence. The rendezvous procedure was a masterpiece of orbital mechanics. As Eagle rose, its guidance system, using the same primitive computer that had nearly failed during descent, adjusted their path with bursts from small attitude thrusters. Collins, watching through Columbia's sextant, finally spotted Eagle as a bright speck against the charcoal gray lunar surface. The two spacecraft danced closer, their movements measured in fractions of inches per second, until, with a gentle bump, the docking latches engaged. The transfer of Armstrong and Aldrin back to Columbia, along with their precious cargo of lunar samples, was a delicate operation, conducted in weightlessness, each movement calculated to avoid contaminating the command module with lunar dust that might damage its systems. With the lunar module cast adrift, its job complete, the three astronauts prepared for trans-Earth injection, the engine burn that would free them from lunar orbit and set them on a course for home. This maneuver had to be timed perfectly. Too early, and they might overshoot Earth. Too late, and they could fall short. When the service module's engine ignited, it pushed the astronauts back into their couches with surprising force, a reminder that even in the airless void of space, Newton's laws remained in full effect. As Earth grew larger in their windows, the crew faced one final challenge: re-entry. The command module had to hit Earth's atmosphere at precisely the correct angle. Too steep, and it would burn up. Too shallow, and it would skip off into space like a stone across a pond. The heat shield, designed to ablate, or burn away, in controlled fashion, would experience temperatures hot enough to melt steel as it converted their tremendous speed into heat and light. The final descent was a symphony of physics. First, the orange glow of ionized air surrounding the capsule, then the buildup of G-forces pressing the astronauts into their couches, followed by the violent jolt of parachutes deploying at 25,000 feet. When Columbia splashed down in the Pacific Ocean, bobbing in the waves like a cork, the mission that had begun 8 days earlier with a thunderous launch was complete. The recovery team from the USS Hornet rushed to secure the capsule, their biological isolation garments a stark reminder that no one yet knew whether the moon harbored dangerous microbes. As the astronauts were whisked away to quarantine, the world celebrated what seemed like the culmination of a journey, But in truth, Apollo 11 was just the beginning, the first fragile connection between two worlds that would lead to new understandings of our solar system's history, inspired generations of scientists and engineers, and forever change humanity's view of its place in the cosmos. The moon was no longer just a light in the sky, but a place humans had touched, studied, and in that brief visit, made part of our shared human story. The fiery launch of Apollo 11 captured the world's imagination, but the mission's true legacy lies in the quiet revolutions it sparked here on Earth. Revolutions so profound they transformed daily life while remaining virtually invisible to the public eye. As the astronauts walked the lunar surface, an army of scientists and engineers back home were already adapting space-age solutions to earthly problems, creating a ripple effect that would touch nearly every aspect of modern existence. At the heart of this transformation was the Apollo guidance computer, a device that represented nothing less than the birth of modern computing. While today we carry processors millions times more powerful in our pockets, the AGC's real breakthrough wasn't in raw capability, but in its revolutionary architecture. The computer's rope memory, literally woven by hand by teams of factory workers threading copper wires through magnetic cores, was the precursor to modern solid-state memory. Its real-time operating system, developed by Margaret Hamilton's team at MIT, introduced concepts like asynchronous processing and priority scheduling that became the foundation from everything from air traffic control systems to smartphone operating systems. The AGC software engineering principles were so advanced that when Hamilton's team later adapted them for medical equipment, they helped create the first reliable digital life support systems for hospitals. The materials science revolution sparked by Apollo was equally transformative. The need to shield astronauts from temperature swings ranging from -250 Fahrenheit to 250 Fahrenheit led to the development of multi-layer insulation, thin sheets of aluminized mylar that now protect everything from newborn babies in incubators to long-distance pipelines in Arctic regions. The same reflective coatings that kept the lunar module from overheating now align emergency shelters for disaster victims. Even the humble memory phone, originally created to improve crash protection for astronauts, found its way into mattresses, shoes, and wheelchair seats, improving comfort and preventing pressure sores for millions. Perhaps the most unexpected technological offspring came from Apollo's power systems. The fuel cells that provided electricity and drinking water for the crew became the prototype for clean energy solutions now being deployed to power homes and vehicles. The silver zinc batteries developed for the astronauts' portable life support systems evolved into the rechargeable batteries that power our laptops and electric cars. And the solar panels tested on later Apollo missions laid the groundwork for today's solar energy revolution. The photovoltaic cells on your neighbor's roof share direct lineage with those that powered the lunar surface experiments. The medical field benefited enormously from Apollo's innovations. The miniaturized biosensors developed to monitor the astronauts' vital signs became the foundation for modern patient monitoring systems. The compact, low-power circuits designed for spaceflight now pace the hearts of cardiac patients worldwide. Even the techniques developed to sterilize spacecraft to prevent lunar contamination found new purpose in hospital operating rooms, helping reduce surgical infections. NASA's work on nutrient preservation for space food led to freeze-drying techniques that revolutionized emergency medicine. Today's lightweight, shelf-stable medical supplies and military rations all trace their origins to Apollo-era research. The imaging technology developed for Apollo created entire new industries. The charge-coupled devices created to capture high-resolution images of the lunar surface became the basis for digital cameras, medical imaging devices, and smartphone cameras. The image enhancement techniques developed to study moon rocks are now used in everything from satellite weather forecasting to early cancer detection. Even the humble CMOS sensor in your phone's camera exists because of the push to make imaging systems smaller and more energy efficient for space missions. Perhaps most profound were Apollo's contributions to systems engineering and project management. The techniques developed to coordinate 400,000 people across 20,000 companies, keeping every component on schedule and within specifications, became the blueprint for managing complex projects from skyscraper construction to global supply chains. The fault tree analysis method invented for Apollo safety checks is now standard practice in industries ranging from nuclear power to commercial aviation. The rigorous testing protocols developed for space hardware raised quality standards across manufacturing. When you board a modern airliner, you're benefiting from safety systems born from Apollo's failure is not an option philosophy. The environmental monitoring systems created for Apollo had unexpected earthbound applications. The gas chromatographs, developed to analyze lunar soil samples, became the basis for modern pollution monitoring equipment. The water purification systems created for the spacecraft evolved into compact filtration units used in disaster zones. Even our understanding of climate change owes a debt to Apollo. The first comprehensive views of Earth from space provided visual proof of our planet's fragility and interconnectedness, fueling the environmental movement. In the realm of daily life, Apollo's influence is equally pervasive. The cordless power tools created for lunar sample collection spawned an entire industry of portable devices. The scratch-resistant lenses developed for helmet visors became the standard for eyeglasses. The moisture-wicking fabrics created for spacesuits revolutionized athletic wear. Even the wireless headsets we take for granted today evolved from the hands-free communication systems developed for astronauts working in bulky suits. Yet, perhaps Apollo's greatest gift was intangible, a fundamental shift in how humanity approaches complex problems. The program proved that no challenge is insurmountable when broken down into manageable components and attacked systematically. This Apollo mindset influenced fields far beyond engineering, from medicine's war on cancer to the digital revolution. The moon landing demonstrated that with sufficient resources, coordination, and determination, humanity could achieve what had previously existed only in the realm of dreams, a lesson that continues to inspire innovators today. As we examine these quiet revolutions, we realize that Apollo's true legacy isn't just in the moon rocks brought back or the flags planted, but in how it reshaped life on Earth in countless subtle ways. The next time you use a cordless device, check your smartphone, or benefit from modern medicine, remember, you're touching pieces of technology that owe their existence to humanity's greatest adventure. Before Apollo 11, the moon was a blank canvas onto which humanity had projected its myths, fears, and scientific conjectures for millennia. Some scientists believed it might be covered in deep dust that would swallow landing spacecraft whole. Others speculated its plains were ancient oceans of molten rock. The 382 kilograms of lunar material returned by the Apollo missions didn't just answer old questions. They revealed an entirely new narrative of our celestial companion's violent, intimate history with Earth, written in the language of isotopes and impact craters. The first revolutionary discovery came from the very dust Armstrong and Aldrin scooped into their sample bags. Under electron microscopes, lunar regolith revealed itself as a treasure trove of tiny glass beads, each a frozen moment of lunar violence. These beads, formed when meteorite impacts melted surface rock that then cooled rapidly in the vacuum of space, contained clues about the moon's volcanic past. Their chemical composition told a story no Earth rock could, of a world where volcanic eruptions occurred not through plate tectonics, which the moon lacks, but through massive outpourings of magma that flooded entire basins. The samples showed these eruptions continued until surprisingly recently, just 1 to 2 billion years ago, rather than the ancient epochs scientists had assumed. The moon rock's most startling revelation came from their oxygen isotopes. When geochemists compared the ratio of oxygen-16 to oxygen-17 in lunar and terrestrial samples, they found an identical fingerprint, a smoking gun proving Earth and Moon shared a common origin. This supported what became the dominant giant impact hypothesis, that early in Earth's history, a Mars-sized body named Theia collided with our planet, vaporizing part of Earth's crust and mantle. The debris from this cosmic catastrophe coalesced in orbit to form the Moon. The Apollo samples allowed scientists to date this event to about 4.51 billion years ago, just 60 million years after the solar system itself formed. The lunar samples also served as cosmic timekeepers. Because the Moon lacks erosion or plate tectonics, its surface preserves impacts from the solar system's most violent era. By dating the glassy melt sheets in lunar craters, scientists reconstructed a timeline of the late heavy bombardment, a period around 4 billion years ago when the inner solar system endured a cataclysmic rain of asteroids and comets. This same bombardment likely sterilized Earth's surface repeatedly, forcing life to either restart or retreat to extreme environments. The Moon thus became a Rosetta Stone for understanding Earth's own missing geological history, the first few hundred million years erased by our planet's restless surface. Apollo seismometers, left on the surface by astronauts, revealed the Moon to be far more geologically alive than anyone expected. The instruments detected thousands of moonquakes annually, some originating hundreds of kilometers deep. These quakes helped map the Moon's internal structure, a crust averaging 50 kilometers thick, compared to Earth's 30-kilometer continental crust, a partially molten mantle, and possibly a small iron core. The seismic data also showed the Moon ringing like a bell after meteorite impacts, a clue to its dry, rigid interior structure, utterly unlike Earth's water-softened geology. One of the most profound discoveries came from the laser retroreflectors placed by Apollo 11, 14, and 15. By bouncing lasers off these mirrors from Earth, scientists made astonishingly precise measurements, showing the Moon is drifting away at 3.8 centimeters per year, a rate that, projected backward, suggests a much closer Moon in Earth's ancient past. This lunar recession explains why prehistoric eclipses don't match calculations based on today's orbit. The Moon was simply too close to Earth billions of years ago to perfectly obscure the Sun. The samples also solved the mystery of the Moon's two-faced nature. The near side we see is dominated by dark volcanic plains, while the far side is all rugged highlands. Apollo showed this dichotomy stems from the Moon's crust being thicker on the far side. When massive impacts later opened basins, only the near side's thinner crust allowed lava to flood them. The samples even preserved traces of the solar wind, giving us our first direct samples of the Sun's composition. Perhaps most remarkably, the Apollo samples continue yielding discoveries half a century later. Modern techniques have detected traces of water in lunar glass beads, water likely delivered by comets during the Moon's fiery youth. Other studies found minerals like tranquilitite and armalachite, named for Apollo 11's landing site and astronauts Armstrong, Aldrin, and Collins, which form only under extreme conditions unknown on Earth. The Moon that emerged from Apollo's studies was no longer the dead, unchanging world of pre-1969 astronomy, but a dynamic partner in Earth's cosmic dance, a witness to the solar system's violent youth, a sculptor of Earth's tides, and possibly even an architect of life's rhythms. Its battered surface became a calendar marking the solar system's most turbulent era, while its chemical kinship with Earth revealed our planet's own violent origins. The Apollo missions did more than rewrite lunar science. They gave us an unprecedented lens through which to understand our own planet's lost history and the fundamental processes shaping all rocky worlds. The Moon's pristine surface, untouched by wind or water, became a mirror reflecting Earth's earliest eons, while its relationship with our planet revealed celestial mechanics operating on timescales beyond human imagination. One of the most profound revelations came from dating the lunar highlands. These ancient crustal rocks, some dating back to 4.4 billion years, showed that the moon had formed a solid surface remarkably early in solar system history. This discovery forced geologists to completely reconsider Earth's formative years. If the moon's crust had solidified so quickly, then Earth, larger and hotter, must have developed its first stable surfaces much earlier than previously believed. The absence of similarly ancient rocks on Earth wasn't evidence of a later formation, rather our planet's relentless geological recycling. The moon thus became the reference point for reconstructing Earth's missing first chapters, the Hadean Eon, from which virtually no terrestrial rocks survive. The lunar samples also preserved a record of cosmic violence that directly impacted Earth's chances for life. The late heavy bombardment period, revealed through Apollo's dating of impact melts, showed that both worlds endured a cataclysmic asteroid rain around 3.9 billion years ago. This explained why Earth's earliest chemical traces of life appear only after this period. The bombardment may have sterilized our planet multiple times, forcing life to either restart or retreat to extreme environments like deep-sea vents. The moon's craters thus became a calibration tool for understanding how frequently large impacts threatened Earth, with implications for both past extinction events and future planetary defense. Apollo's seismometers detected moon quakes, revealing another surprise. The moon still experiences tidal flexing from Earth's gravity. This proved our satellite isn't completely frozen geologically, retaining enough internal heat to occasionally shift its mass. These findings transformed our understanding of how small rocky bodies cool over time, with implications for predicting volcanic activity on moons throughout the solar system. The data even suggested the possible existence of deep magma pockets, a hypothesis that gained support decades later when orbiting spacecraft detected outgassing of radon and polonium. The laser retroreflectors allowed measurements so precise they detected the moon's liquid core sloshing as it orbits, a phenomenon called libration. By tracking these minuscule wobbles, physicists calculated the moon's core is about 20% liquid, surrounded by a partially molten boundary layer. This discovery helped explain why the moon's far side has a thicker crust. Early tidal forces from Earth may have concentrated heat and magma on the near side. Such tidal heating mechanisms are now recognized as key to maintaining subsurface oceans on icy moons like Europa and Enceladus, expanding the potential habitats for extraterrestrial life. The lunar samples also became a Rosetta Stone for planetary science beyond our Earth-Moon system. The way meteorite impacts melted and mixed lunar surface material provided a template for understanding surface evolution on Mercury and asteroids. The discovery of nanoparticles of pure iron in lunar soil explained similar spectral signatures detected on Mercury and some asteroids. Even the study of how solar wind particles become embedded in lunar grains helped develop techniques for analyzing asteroid samples returned by later missions. Perhaps most remarkably, Apollo's lunar samples continue yielding discoveries as analytical techniques advance. In 2020, researchers using atom probe tomography detected water molecules trapped inside glass beads from the Apollo 15 and 17 samples, water that must have been delivered by comets during the moon's early history. This finding forced a reevaluation of how volatiles are distributed and preserved on airless bodies. Other teams have identified carbon isotopes in lunar soils that may represent traces of ancient solar wind composition, providing a window into the young sun's behavior. The moon's relationship with Earth also revealed cosmic connections stretching far beyond our system. The precise laser measurements showed Earth's rotation slowing by 1.7 milliseconds per century due to tidal friction, a change that accumulates dramatically over geologic time. Paleontologists studying growth patterns in fossilized coral confirmed this, finding that 400 million years ago, Earth's day was just 22 hours long, and there were 400 days in a year. These lunar-derived measurements of Earth's changing spin became crucial evidence in studying exoplanets, helping model how tidal forces affect planetary systems throughout the galaxy. The Apollo samples even changed our understanding of Earth's atmosphere. The lunar regolith, exposed to solar wind for billions of years, preserved a record of how the sun's output and our planet's magnetic field have varied over time. By analyzing isotopes like helium-3 implanted in lunar soil grains, scientists reconstructed historical solar activity cycles with implications for understanding climate variation on Earth. The complete absence of weathering on lunar materials also provided the ultimate control sample for studying how Earth's atmosphere and water alter rocks, a reference point essential for identifying potential biosignatures on Mars and other worlds. As we look to future lunar exploration, the Apollo legacy reminds us that each new sample, each instrument left on the surface, becomes a gift to future generations of scientists armed with ever more sophisticated tools. The 6 Apollo landing sites are now recognized as humanity's first off-world archaeological sites, their artifacts and sample locations meticulously documented for ongoing study. The moon has become not just another world to explore, but a partner in understanding Earth's place in the cosmos, a silent witness to 4.5 billion years of shared history, waiting to reveal its next secrets. The Apollo missions did far more than satisfy humanity's curiosity about our celestial neighbor. They fundamentally reshaped our understanding of where and how life might exist in the cosmos. The moon's harsh, airless reality forced scientists to reconsider the basic requirements for life, while its chemical kinship with Earth provided crucial insights into how habitable worlds evolve. What began as geological sampling would ultimately transform astrobiology, guiding our search for life from Mars's deserts to Europa's hidden oceans. The first paradigm shift came from what the moon lacked. Analysis of Apollo samples revealed no trace of organic compounds or fossilized microorganisms, the definitive proof that not all rocky worlds automatically host life. This stark lifelessness, contrasted with Earth's teeming biosphere, highlighted how rare and precious our planet's combination of factors truly is. Yet, simultaneously, the discovery of water-bearing minerals in some lunar samples hinted that even airless bodies might preserve the ingredients necessary for life, if not life itself. These contradictory findings framed one of astrobiology's central questions. What precise combination of geology, chemistry, and celestial circumstances transforms mere habitability into actual inhabitation? The moon's extreme environment became a testing ground for life's limits. Scientists were astonished to find that certain terrestrial microbes, when embedded in simulated lunar soil, could survive vacuum and radiation conditions similar to the moon's surface. This discovery expanded our conception of potentially habitable zones in the solar system, suggesting that microbial life might persist in more extreme environments than previously imagined. The Apollo samples also demonstrated how meteorite impacts could launch potentially life-bearing rocks between worlds. Lunar material showed clear evidence of having been shocked, but not fully melted during impacts, preserving its original chemistry. This supported the theory of panspermia, the idea that life's building blocks might travel between planets aboard meteorites. Perhaps most importantly, Apollo provided the first off-world reference point for comparative planetology. By studying how solar radiation and micrometeorites alter lunar surface material, scientists developed techniques to distinguish between abiotic chemical processes and potential biosignatures, a crucial toolkit now used in analyzing Mars rover data. The complete absence of weathering on lunar rocks established the baseline for what purely geological processes look like, making it easier to identify possible biological anomalies in meteorites and planetary samples. The moon's influence on astrobiology extended to its role in stabilizing Earth's environment. Precise laser measurements from Apollo's retroreflectors confirmed that the moon's gravitational pull maintains Earth's axial tilt within habitable limits. Without our large moon, Earth's tilt would vary chaotically over geological time, causing extreme climate swings that could prevent complex life from developing. This realization made astronomers reconsider what makes a planet truly habitable. Not just the presence of water and atmosphere, but the entire celestial context, including planetary satellites. Apollo's discoveries directly shaped subsequent missions searching for extraterrestrial life. The Viking landers sent to Mars in 1976 carried experiments designed with lunar experience in mind. Their gas chromatograph mass spectrometers were upgraded versions of instruments first tested on lunar samples. When Martian meteorites were later found on Earth, scientists used techniques developed for Apollo samples to analyze them, leading to the controversial but influential 1996 claim of possible fossilized microbes, a claim that galvanized the field of astrobiology despite remaining unproven. The search for life on icy moons like Europa and Enceladus also owes much to Apollo. Studies of how the moon's interior retains heat despite its small size helped model how tidal forces could maintain subsurface oceans on distant moons. The discovery of water molecules in lunar glass beads suggested how volatiles might be preserved on airless bodies, informing strategies for sampling plumes from Enceladus's cryovolcanoes. Even the Lunar Reconnaissance Orbiter's findings of hydrogen deposits at the moon's poles, possible water ice preserved in permanent shadows, echoed the Apollo's initial detection of trace water and guided the targeting of later missions. Today, as Artemis missions prepared to return humans to the moon, astrobiological questions dominate the scientific agenda in ways Apollo planners never imagined. New instruments will search for organic compounds in permanently shadowed craters that may have collected cometary material over billions of years. Advanced spectrometers will probe whether the moon preserves traces of Earth's earliest atmosphere, blown off by solar wind and deposited on the lunar surface, a potential window into the environment where life first emerged on our planet. The Apollo missions began as a political and technological endeavor, but ultimately became humanity's first step in answering its most profound question: are we alone in the universe? By showing us what a lifeless world looks like up close, the moon taught us what to seek and what to avoid in our search for cosmic companions. Every exoplanet study, every Mars drill sample, every analysis of Europa's plumes builds upon the foundational knowledge gained from those 382 kilograms of lunar rock. The moon, once thought to be a dead end in the search for life, has become our most valuable guide in exploring the potential for life elsewhere. The footprints left by Apollo astronauts in the lunar dust were never meant to be permanent. Over decades, solar radiation and micrometeorite impacts would have erased their delicate impressions, yet their legacy endures, not just in museum displays or history books, but in the new generation of spacecraft now retracing their path to the moon. The Artemis program, international lunar missions, and commercial landers all carry forward the torch lit by Apollo, building upon its discoveries while confronting new questions that could only emerge after humanity's first tentative steps on another world. The differences between the 1960s lunar program and today's efforts reveal just how profoundly Apollo transformed our understanding of space exploration. Where Apollo relied on government funding and purely national expertise, Artemis embraces international partnerships and commercial innovation. The Lunar Gateway Station, taking shape in orbit, will host astronauts from multiple nations, while private companies develop robotic landers to deliver payloads across the moon's surface. This collaborative approach stems directly from Apollo's most important lesson, that lunar exploration is too vast, too complex, and too meaningful for any single entity to undertake alone. Scientific priorities have evolved dramatically since Apollo's era. While the first missions focused on basic geology and proving human survival, Artemis targets the moon's most enduring mysteries: its polar water ice, its underground lava tubes, and its potential as a platform for cosmic observation. The discovery of water molecules in Apollo samples, once dismissed as contamination, now drives mission architecture. New spectrometers will map hydrogen concentrations across permanently shadowed craters where temperatures never rise above -250 degrees Fahrenheit, preserving ancient ice that could reveal the solar system's water history and provide resources for future explorers. Technology has transformed equally dramatically. Apollo's astronauts relied on paper maps and ground-based calculations. Artemis crews will navigate with lunar GPS satellites and terrain-relative autonomous landing systems. Where Apollo's lunar module had the computing power of a pocket calculator, today's spacesuits feature augmented reality displays that overlay navigation data and system diagnostics onto helmet visors. Even the approach to lunar construction has evolved. NASA and ESA are testing 3D printing using simulated lunar regolith, while robotics companies develop autonomous bulldozers to prepare landing sites. Perhaps most significantly, our understanding of lunar hazards has matured. Apollo's short surface missions faced dust problems. The razor-sharp regolith clung to everything and degraded seals. But Artemis must contend with month-long stays during which dust inhalation could pose serious health risks. New electrostatic removal systems and ultra-smooth suit materials aim to solve this decades-old challenge. Radiation protection has also advanced, with water-filled walls and underground habitats proposed to shield crews during solar storms, solutions informed by Apollo's radiation measurements, but made urgent by plans for extended stays. The Moon's role as a proving ground for Mars has come into sharp focus. Where Apollo was seen as a destination, Artemis treats the Moon as a classroom, testing life support systems, surface habitats, and resource utilization techniques needed for the red planet. The Moon's night duration of 2 weeks mirrors Martian dust storms' timeline, while the Moon's 1/6 gravity provides a reasonable approximation of Mars's 1/3. Even the psychology of lunar missions now serves as preparation, with isolation studies in Antarctic bases and underwater habitats refining our understanding of crew dynamics for longer journeys. International ambitions have expanded the lunar exploration landscape in ways unimaginable during Apollo. China's Chang'e program has deployed rovers to the far side and returned samples from previously unexplored regions. India's Chandrayaan missions mapped water ice distribution, while South Korea's Danuri orbiter studies magnetic anomalies. These missions aren't replicating Apollo, they're building upon it, investigating questions the early missions couldn't address with their limited time and technology. The Moon has become a global laboratory, with each nation contributing unique instruments and perspectives to humanity's collective understanding. Commercial involvement represents perhaps the most radical departure from Apollo's model. Where NASA once designed and built every component, today private companies develop lunar landers, rovers, and even propose tourist habitats. This shift reflects another Apollo lesson, that sustainable exploration requires economic viability beyond government funding. Startups are testing technologies to extract oxygen from lunar soil, while aerospace firms develop reusable lunar landers that could dramatically reduce costs. The Moon is no longer just a scientific destination, but a potential marketplace for research, for resources, and eventually for human experience. Yet, for all these changes, Artemis carries forward Apollo's most essential legacy, the understanding that lunar exploration is ultimately about more than rocks and radiation measurements. It's about pushing the boundaries of human capability, about developing technologies that improve life on Earth, and about inspiring new generations to look upward. The children who watched Apollo landings became the scientists and engineers behind today's space programs. The students following Artemis may become the first Martians or the discoverers of life beyond Earth. As new spacecraft race toward the Moon, they follow a path illuminated by Apollo's triumphs and tempered by its limitations. The first lunar program showed us what was possible. The next will show us what's sustainable. Where Apollo planted flags, Artemis aims to plant roots. not just visiting another world, but learning to live there. The moon that revealed its geological secrets to Apollo astronauts now prepares to teach us even deeper lessons about humanity's future as a spacefaring species. As we bring our celestial voyage to a close, we find ourselves suspended between two worlds, the familiar blue marble of Earth and the silvery cratered visage of our moon, now transformed in our collective consciousness from distant celestial body to tangible destination. The story of Apollo and its unfolding sequel in Artemis represents more than just a chronicle of technological achievement. It is the narrative of humanity's most profound relationship with another world, one that has shaped our past and will inevitably define our future. The moon has been our silent companion through the entirety of human existence, its phases marking time before calendars, its glow illuminating the nights of countless generations. Yet, in the mere 6 decades since we first reached out and touched its surface, our understanding of the celestial neighbor has undergone a revolution as profound as any in human history. Those first blurred television images of Armstrong's boots sinking into the lunar regolith did more than document a moment. They shattered forever the psychological barrier between Earth and the cosmos, proving that worlds which had existed only in imagination and telescope lenses could become places where humans walked, worked, and wondered. What began as a political competition between superpowers has blossomed into something far more enduring, a sustained global effort to understand and utilize our nearest celestial neighbor. The Apollo program's greatest legacy may not be the 842 pounds of lunar samples or the thousands of photographs, but rather the paradigm shift it created in how humanity views its place in the universe. The famous Earthrise photograph, taken during Apollo 8's lunar orbit, became the iconic representation of our planet's fragility and unity, sparking the environmental movement and giving visual form to the concept of Spaceship Earth. This shift in perspective, this cosmic consciousness, is perhaps Apollo's most precious gift to civilization. The scientific returns from Apollo continue to accumulate even today, like interest on an intellectual investment made half a century ago. Modern analytical techniques, undreamed of in the 1960s, continue to tease new secrets from those carefully curated lunar samples. Atom-by-atom analysis now reveals traces of water and minerals once thought to be bone dry, while isotopic studies uncover new clues about the moon's violent formation. The passive experiments left on the surface, the laser retroreflectors that still return photons to Earth, the seismometers that recorded moonquakes until 1977, have provided decades of data that continue to refine our understanding of lunar and planetary science. The footprints left by Apollo astronauts in the lunar dust were never meant to be permanent. Over decades, solar radiation and micrometeorite impacts would have erased their delicate impressions, yet their legacy endures, not just in museum displays or history books, but in the new generation of spacecraft now retracing their path to the moon. The Artemis program, international lunar missions, and commercial landers all carry forward the torch lit by Apollo, building upon its discoveries while confronting new questions that could only emerge after humanity's first tentative steps on another world. The differences between the 1960s lunar program and today's efforts reveal just how profoundly Apollo transformed our understanding of space exploration. Where Apollo relied on government funding and purely national expertise, Artemis embraces international partnerships and commercial innovation. The Lunar Gateway Station, taking shape in orbit, will host astronauts from multiple nations, while private companies develop robotic landers to deliver payloads across the moon's surface. This collaborative approach stems directly from Apollo's most important lesson, that lunar exploration is too vast, too complex, and too meaningful for any single entity to undertake alone. Scientific priorities have evolved dramatically since Apollo's era. While the first missions focused on basic geology and proving human survival, Artemis targets the moon's most enduring mysteries, its polar water ice, its underground lava tubes, and its potential as a platform for cosmic observation. The discovery of water molecules in Apollo samples, once dismissed as contamination, now drives mission architecture. New spectrometers will map hydrogen concentrations across permanently shadowed craters where temperatures never rise above -250 degrees Fahrenheit, preserving ancient ice that could reveal the solar system's water history and provide resources for future explorers. Technology has transformed equally dramatically. Apollo's astronauts relied on paper maps and ground-based calculations. Artemis crews will navigate with lunar GPS satellites and terrain-relative autonomous landing systems. Where Apollo's lunar module had the computing power of a pocket calculator, today's spacesuits feature augmented reality displays that overlay navigation data and system diagnostics onto helmet visors. Even the approach to lunar construction has evolved. NASA and ESA are testing 3D printing using simulated lunar regolith, while robotics companies develop autonomous bulldozers to prepare landing sites. Perhaps most significantly, our understanding of lunar hazards has matured. Apollo's short surface missions faced dust problems. The razor-sharp regolith clung to everything and degraded seals. But Artemis must contend with month-long stays during which dust inhalation could pose serious health risks. New electrostatic removal systems and ultra-smooth suit materials aim to solve this decades-old challenge. Radiation protection has also advanced, with water-filled walls and underground habitats proposed to shield crews during solar storms, solutions informed by Apollo's radiation measurements, but made urgent by plans for extended stays. The Moon's role as a proving ground for Mars has come into sharp focus. Where Apollo was seen as a destination, Artemis treats the Moon as a classroom, testing life support systems, surface habitats, and resource utilization techniques needed for the red planet. The Moon's night duration of 2 weeks mirrors Martian dust storms' timeline, while the Moon's 1/6 gravity provides a reasonable approximation of Mars's 1/3. Even the psychology of lunar missions now serves as preparation, with isolation studies in Antarctic bases and underwater habitats refining our understanding of crew dynamics for longer journeys. International ambitions have expanded the lunar exploration landscape in ways unimaginable during Apollo. China's Chang'e program has deployed rovers to the far side and returned samples from previously unexplored regions. India's Chandrayaan missions mapped water ice distribution, while South Korea's Danuri orbiter studies magnetic anomalies. These missions aren't replicating Apollo, they're building upon it, investigating questions the early missions couldn't address with their limited time and technology. The Moon has become a global laboratory, with each nation contributing unique instruments and perspectives to humanity's collective understanding. Commercial involvement represents perhaps the most radical departure from Apollo's model. Where NASA once designed and built every component, today private companies develop lunar landers, rovers, and even proposed tourist habitats. This shift reflects another Apollo lesson, that sustainable exploration requires economic viability beyond government funding. Startups are testing technologies to extract oxygen from lunar soil, while aerospace firms develop reusable lunar landers that could dramatically reduce costs. The Moon is no longer just a scientific destination, but a potential marketplace for research, for resources, and eventually for human experience. Yet, for all these changes, Artemis carries forward Apollo's most essential legacy, the understanding that lunar exploration is ultimately about more than rocks and radiation measurements. It's about pushing the boundaries of human capability, about developing technologies that improve life on Earth, and about inspiring new generations to look upward. The children who watched Apollo landings became the scientists and engineers behind today's space programs. The students following Artemis may become the first Martians or the discoverers of life beyond Earth. As new spacecraft race toward the moon, they follow a path illuminated by Apollo's triumphs and tempered by its limitations. The first lunar program showed us what was possible. The next will show us what's sustainable. Where Apollo planted flags, Artemis aims to plant roots, not just visiting another world, but learning to live there. The moon that revealed its geological secrets to Apollo astronauts now prepares to teach us even deeper lessons about humanity's future as a spacefaring species. As we bring our celestial voyage to a close, we find ourselves suspended between two worlds: the familiar blue marble of Earth and the silvery, cratered visage of our moon, now transformed in our collective consciousness from distant celestial body to tangible destination. The story of Apollo and its unfolding sequel in Artemis represents more than just a chronicle of technological achievement. It is the narrative of humanity's most profound relationship with another world, one that has shaped our past and will inevitably define our future. The moon has been our silent companion through the entirety of human existence, its phases marking time before calendars, its glow illuminating the nights of countless generations. Yet in the mere 6 decades since we first reached out and touched its surface, our understanding of this celestial neighbor has undergone a revolution as profound as any in human history. Those first blurred television images of Armstrong's boot sinking into the lunar regolith did more than document a moment. They shattered forever the psychological barrier between Earth and the cosmos, proving that worlds which had existed only in imagination and telescope lenses could become places where humans walked, worked, and wondered. What began as a political competition between superpowers has blossomed into something far more enduring, a sustained global effort to understand and utilize our nearest celestial neighbor. The Apollo program's greatest legacy may not be the 842 pounds of lunar samples or the thousands of photographs, but rather the paradigm shift it created in how humanity views its place in the universe. The famous Earthrise photograph taken during Apollo 8's lunar orbit became the iconic representation of our planet's fragility and unity, sparking the environmental movement and giving visual form to the concept of spaceship Earth. This shift in perspective, this cosmic consciousness, is perhaps Apollo's most precious gift to civilization. The scientific returns from Apollo continue to accumulate even today, like interest on an intellectual investment made half a century ago. Modern analytical techniques, undreamed of in the 1960s, continue to tease new secrets from those carefully curated lunar samples. Atom-by-atom analysis now reveals traces of water in minerals once thought to be bone dry, while isotopic studies uncover new clues about the moon's violent formation. The passive experiments left on the surface, the laser retroreflectors that still return photons to Earth, the seismometers that recorded moonquakes until 1977, have provided decades of data that continue to refine our understanding of lunar and planetary science. As we stand on the threshold of the Artemis era, we see Apollo's legacy manifest in surprising ways. The lunar landers, being developed by private companies, owe their existence to the entrepreneurial space economy that Apollo's technology helped create. The international partnerships forming around lunar exploration grew from Apollo's demonstration that such achievements require global cooperation. Even the environmental movement to protect historic lunar landing sites stems from our dawning realization that humanity's first steps on another world represent a cultural heritage as significant as any terrestrial archaeological treasure. The moon of our future will be very different from the one Apollo revealed. Where Apollo astronauts found a pristine, untouched world, Artemis crews will discover a moon already bearing human marks. Not just the descent stages and flags of Apollo, but likely the robotic landers and rovers of multiple nations. This presents both challenges and opportunities: the need to preserve historically significant sites while enabling new exploration, the balance between scientific study and economic utilization, the careful management of lunar resources that belong, in some sense, to all humanity. Perhaps most importantly, a relationship with the moon has become reciprocal. No longer just an object of study, the moon is becoming a partner in humanity's cosmic journey, a platform for astronomy with its radio-quiet far side, a testing ground for technologies needed to live on Mars, a potential source of resources, including water and helium-3. The lunar lava tubes that may one day shelter astronauts from radiation were unknown in Apollo's day. The water ice at the poles that could support sustained exploration was merely theoretical. Our expanding knowledge makes each return to the moon not a repetition, but a revelation. The children who watched Apollo landings on black and white televisions became the scientists and engineers who built the Space Shuttle and International Space Station. Today's students following Artemis will become the Mars explorers and perhaps the first interstellar travelers. This continuity across generations, this passing of the cosmic torch, is Apollo's living legacy, more enduring than any hardware left on the lunar surface. As we conclude this journey through humanity's lunar saga, we recognize that the moon has become something more than rock and dust orbiting Earth. It is now a symbol of what our species can achieve when curiosity, determination, and imagination align. It serves as a reminder that no frontier is forever beyond reach, that no challenge is insurmountable when faced with sustained effort and collective will. The moon that watched over the birth of civilization now awaits our return, not as visitors this time, but as residents and stewards. The same face that inspired myths and guided navigators will soon witness lunar bases and perhaps cities, their lights twinkling beside the eternal glow of Earthshine. In this coming era, humanity will truly become a multi-world species, with the moon as our first foothold in the cosmos. So let us end not with farewell, but with anticipation. The greatest lunar stories are yet to be written, in the research stations of Artemis, in the laboratories analyzing new samples, in the minds of young people who will see moon landings not as history, but as current events. The Apollo chapter may be complete, but humanity's lunar story has only just begun. As you gaze at the moon tonight, remember it is no longer just a world to observe, but one we have touched, one that has touched us in return, and one that awaits our next visit with the patience of geologic time. The moon has been our companion through all of human history. Now it becomes our destination, our classroom, and perhaps eventually our home. Good night, and may your dreams carry you moonward, to the landing sites of the past, the bases of the present, and the possibilities of the future.